So on our list of examples, the next group that we want to talk about are the SP2NR groups. So the SP2NR groups are important for classical mechanics. Now, in classical mechanics, remember that if we have a system with n degrees of freedom, so we have a classical system, which has n degrees of freedom, so what do I mean by n degrees of freedom? So for example, if I have a particle in three-dimensional space, then its coordinates, it's given by three coordinates, right? So then it would have 3 degrees of freedom. So similarly, suppose that we have some complicated system where there are more than one particle and there are some constraints relating the particles. So the number of degrees of freedom would not be a simple 3n times the 3 times the number of particles. It could be some general integer n. So let's just keep things general. So we have n degrees of freedom. So another way of putting it is by n, I mean there are n generalized coordinates. So for example, if I have like a simple harmonic oscillator in 2 dimensions, so we have an oscillator, a pendulum which is free to swing in a 2-dimensional plane. So but it follows the arc of a circle as it oscillates. So superficially, the position of the bob of the pendulum is given by 2 numbers. But we know that because the bob of the pendulum is constrained to move on a circle, it's actually adequately and accurately described by just one number, an angle theta. So this is an example of a system which has only 1 degree of freedom. So in classical mechanics, if we have a system with n degrees of freedom, then at any given moment, the state of the system is represented by a point on a 2n dimensional space called the phase space. So the complete state of a classical system which has n, let's say, generalized coordinates is represented by a point in a 2n dimensional space called the phase space. Okay, so what are the extra n dimension of phase space? Well, they are what is known as the canonically conjugate momenta. So suppose this is our phase space, and we have the generalized coordinates in this direction. So these are the QIs. Then in the other direction, we are going to have PIs. So PIs, okay, so what are these things? QIs are the generalized coordinates. Whereas the PIs are the canonically conjugate momenta. And there are many ways to define the canonical conjugate momenta, but the actual definition is that PI is given by the partial derivative of the Lagrangian of the system respect to QI dot, the dot being the time derivative. So QI dot is d of QI by dt. Okay? So this is the phase space, and if I give you the state of the system, it is just given by a point on the phase space. As we know that Newton's law is a second order ODE, and therefore if I have a system with n degrees of freedom, I will need 2n boundary conditions to specify its evolution. And that's exactly how many degrees of freedom or how many axes the phase space has. So this is phase space. So if I now define the Hamiltonian of the system, so the Hamiltonian is the energy function of the system, then the Hamiltonian, it can be shown, defines naturally on the phase space a vector field. So what is a vector field? A vector field is a specification of a small vector at every point in the space. So example of a vector field would be, say, the vector field of wind flow on the surface of the Earth. We can associate a small vector whose direction would be the direction of the wind, and the magnitude would be proportional to the strength of the wind, the wind velocity, wind speed. So that's an example of a vector field. So the Hamiltonian, it can be shown using the machinery of classical mechanics, specifies a vector field. And the vector field, I'm drawing something very random here, but the vector field itself can have all kinds of shapes. Okay, and there are vectors at every point. So given such a vector field, what happens is that these vectors are tangent to some curves. And these curves are known as integral curves. Okay, so all these, all these small vectors, they form a continuous sort of, they are tangent vectors to these integral curves. And so what happens is that, when a point with the state of the system falls on one of these integral curves, what it does is that its evolution is determined by the small vector fields. So essentially, the point then moves around in the phase space following these little vectors. Okay. So this is basically kind of the geometry of the phase space. So every point in a phase space is essentially given by some vector. So this is a different vector from the vector field. This is just a column matrix, which consists of, say, the generalized coordinates and the canonical conjugate momenta. So this V gives us a point in the phase space. So Hamilton's equation, which are basically Newton's equation but formulated in terms of phase space, it involves an antisymmetric two form. So it involves an antisymmetric two form, which is known as omega. So what is a two form? A two form is, so let me call this phase space, say, P. So the Hamilton's equation involves a two form which maps us from, say, 2 points on the phase space. So this should be P, not F, to a point in R. So the way this works is that, we have some point from the phase space, say V1, and so this two form takes two of these points and spits out a number. But Hamilton's equations have a symmetry. And the symmetry is that there are these transformations called canonical transformations, which if we represent them by matrices, there's a matrix G acting on V1, and the same matrix G acting on V2, then it leaves this two form invariant. So this turns out these matrices form a group. And these matrices form a group which is for a system of n degrees of freedom, this group is called sp2n, R, where sp stands for symplectic. This is also called a symplectic group. So let me show you what the symplectic matrices look like for the most basic, for the classical mechanical system with the fewest number of degrees of freedom. So suppose our phase space has two coordinates. So our V has only one generalized coordinate Q, and P is the canonically conjugate momentum. So for example, the simple harmonic oscillator would be an example of such a system. Of course, we know that for the simple harmonic oscillator, the integral curves are closed curves, right? They're essentially, because it's a periodic system, so they're closed curves. So what we do is that we take this V and we plug it into this equation. Now there's another theorem in classical mechanics, and that theorem is called Darboux's theorem. And what that theorem says is that locally we can always find some coordinates such that the two form omega can be represented as a matrix like this. So for our case, so let me just choose the signs according to my convenience. So Darboux's theorem says that the two form can always be chosen in this way. Okay, so now if I look at the definition of the symplectic group, which is this thing, then what do we get? We should basically get that, so V is QP, and V prime is some other Q prime P prime, and then Darboux's theorem is telling us that omega is 0, 1, minus 1, 0. And now if I represent my 2 by 2 matrix by, say, alpha, beta, gamma, delta, where alpha, beta, gamma, delta are real numbers, then basically what we have is that this equation, omega v comma v prime equal to omega g acting on v and g acting on v prime. This equation becomes, because v and v prime are arbitrary, this equation becomes alpha beta, gamma, delta, that's a matrix, its transpose, and then 0, 1, minus 1, 0, and then alpha, beta, gamma, delta, that's equal to 0, 1, minus 1, 0. Okay, so if you now work this out, what happens is the left-hand side just becomes 0, alpha, delta, minus beta, gamma, and then minus alpha, delta, plus beta, gamma, 0. This is equal to 0, 1, minus 1, 0. So this becomes that the determinant of the matrix alpha, beta, gamma, delta is plus 1. So this is the condition that the SP2, R matrices have to satisfy. Now, incidentally, see that this is also the condition for the group, which is SL2R. So for n equals to 2, n equals to 1, SP2R is equal to SL2R. So this need not be the case in higher dimensions. Okay, this is an accident of lower dimension. Now let's look at the generators of SP2R. So the generators of SP2R, so to find them out, let's just represent an element of SP2R by exponential times lambda L, where lambda is a real number and L is some matrix. And then, what we do is that we take that equation that G has to satisfy. So we have G transpose 0, 1, minus 1, 0, G is equal to 0, 1, minus 1, 0. And then we take its derivative and set that equals to 0. Well, that is, this we are taking the derivative of an equation, and then set the value of the parameter lambda to 0. So if I do this, I get an equation for L. And that equation is L transpose 0, 1, minus 1, 0, plus 0, 1, minus 1, 0, L is 0. Okay. So if I now represent L, the matrix L, what this does is that it puts a constraint on the matrix. It says that the matrix has to be trace-free. So the matrix has to be A minus A, B, C. This has to be the form of the matrix. And as we can see, we cannot further constrain the matrix because we are already down to 3 parameters, A, B, and C. And we know that SL2R is a 3-dimensional group. And therefore, SP2R is also a 3-dimensional group. So we can now choose the generators of SP2R. So these are the generators of SP2R. They are E, 0, 1, 0, 0. F is 0, 0, 1, 0. G, 1, 0, 0, minus 1. Okay, so these are the generators. And so from these generators, we can now derive the Lie group, the Lie algebra, sorry. So the Lie algebra is going to be the commutator of E and F is G. The commutator of G and E is 2E. And the commutator of G and F is minus 2F. Okay. So this is what the Lie algebra looks like. Now let's look at the subgroups of SP2R. So an obvious subgroup of sp2r is that if I take G, remember G is a diagonal matrix. So if I keep on multiplying G by itself, we keep on getting a diagonal matrix. So if I exponentiate G, then I get e to the power t 0, 0, e to the power minus t. And we can see t can take any values, and therefore, this is, this group is going to be, this is going to be a positive number, right? So one of the things that it shows is that because t is a parameter which takes its value in R, it shows that this is a non-compact group, right? That sp2R is a non-compact group. Okay, what about any other subgroups? There's another subgroup of sp2R which is generated by E minus F. So if I take E to the power theta, E minus F, then it can be shown that this is just nothing but cosine of theta minus sine of theta, sine of theta, cosine of theta, which is nothing but the group SO2, right? So now we can generalize the symplectic group to n dimensions. So, so generalize these ideas. sp2nr. In that case, we have to solve the condition G transpose 0, 1, minus 1, 0, G equal to 0, 1, minus 1, 0. So these are block matrices, and they are all n by n matrices, so that the whole matrix is 2n by 2n, and these are 2n by 2n matrices. And again, if we now solve for the generators of this group, then these are 2n by 2n matrices, the generators, and the generators will have the form that there's an n by n matrix along the diagonal, and on the off diagonal there'll be two more matrices, B and C, and both B and C must be orthogonal, symmetric matrices. Okay. Now you can show that the dimension, and I leave it as an exercise, and just from this and these relationships, you can show the dimension of sp2n of R is 2n squared plus n. Okay, so let's just put n equals to 1. If n equals to 1, then we have 2 times 1 plus 1, which is 3, which matches with what we just saw. So this is where we end our discussion of the sp2n groups. In the next lecture, we shall look at the Heisenberg group and the Poincare group.